Okay, so today, everybody, we're going to get into the mathematical side of acids and bases, and there's a whole bunch of things that we have to work through, kind of some foundational types of things that we have to do before we get into the really complex problems that are associated with acids and bases. So, from a foundation perspective, you have to know a couple of things. Number one, you have to know the relationship between hydronium concentration, hydroxide concentration, their relationship with Kw. And then you also need to know the relationship between those two concentrations and also pH and pOH. So that'll be next class, as a matter of fact. So today we're just going to address the concentrations of hydronium and hydroxide in a solution and the value of Kw. Okay, so that's kind of the plan for today. You can see over my shoulder here kind of the things that we're going to go through. Shouldn't be a super long one. You'll see that next class is about the pH and pOH. So first thing, let's review real quick the water equilibrium and K expression for that equilibrium and where it's coming from and what we're using to do a calculation. So water's equilibrium, if you recall, water doesn't actually dissociate like an Arrhenius substance. It actually, two water molecules bump into each other and they exchange an H+. And that's the Bronsted-Lowry definition of how it all works. So the equilibrium was two water molecules in liquid form in equilibrium with a hydronium ion and a hydroxide ion. And the hydronium and the hydroxide get made in a one-to-one relationship. So when two water molecules bump into each other, H plus goes from one to the other. And that's kind of dependent on how it's hitting and the force that it's hitting. Mostly the geometry, to be honest with you. And then you make hydronium and hydroxide. If you have distilled water, meaning pure water at whatever temperature it's at, you will always produce hydronium and hydroxide in a one-to-one ratio. Therefore, the concentrations will always be the same if you have distilled water, regardless of the temperature. Okay, so those two concentrations are going to be the same. Now, they're small. Water doesn't do this a ton, and it's not that there's not a lot of collisions between water molecules. It's just that the products of that chemical reaction, as you can see, hydronium and hydroxide, because they're oppositely charged, they have a tendency to come back together again. So the collisions aren't so random. So they'll actually go in the reverse direction really quickly, which means that not very many water molecules are in the ion form. Okay, so the term for that process is called ionization. So water does not ionize terribly well, and because the ions come back together and they form the neutral water molecules. Okay, so that's kind of the general gist. Because of that, we have a very low equilibrium constant. So Kw, if we recall from last class, Kw, which is the equilibrium constant for water, is calculated by taking the concentration of the products over the concentration of the reactants. Well, the reactants are in liquid form, so their concentrations are unchanging, so they're just 1, which means that all we have really in the K expression is the products. So we have the concentration of hydronium times the concentration of hydroxide. Great. As I said last class, that mathematical expression is true for water at any temperature. In any situation, that equilibrium is going on and that K expression exists no matter what. Like it's a mathematical truth that you can say about water. If you have water, you have that equilibrium constant going on. If you have distilled water, meaning you haven't added anything into it, or there isn't some kind of contaminant in there doing other things, reacting with the water or doing some weird kind of wonderful thing, those two concentrations, hydronium and hydroxide, will be the same. And so therefore, if you take the square root of whatever the value of Kw is, you will get the hydronium and the hydroxide concentration. I asked you to memorize in the last class, memorize Kw at 25 degrees, and all of your teachers will ask you to memorize Kw at 25 degrees. Kw at 25 degrees. At 25 degrees Celsius, Kw equals 1.0 times 10 to the negative 14. Critical that you remember that. Okay, so it's going to pop in your head all the time, and so you won't probably actively have to memorize it, but you need to know that number. Okay, so we've reviewed already the equilibrium of water. It has an equilibrium constant. That equilibrium constant's expression is hydronium times hydroxide, which means those two concentrations multiplied together will always give you the constant value of whatever temperature that is. And at 25 degrees, that constant is 1 times 10 to the negative 14. Thinking logically from a mathematical perspective, if that's a constant value and you have something that has made the hydronium concentration go up in water, meaning you've added an acid. If you add an acid, the hydronium is going to go higher. And when hydronium gets to be a higher concentration, what does the hydroxide have to do so that they can still multiply to the same value? Mathematically, if one goes up, the other has to go down so that they still multiply to the same value. Okay? 4 times 2 equals 8. Well, if you change one of those numbers to a 1, well, 1 times 8, one has to go up while the other one has to go down if you're still going to multiply to 8. So if you're talking about 1 times 10 to the negative 14, if one goes up, the other has to go down so that you can still multiply to that same value. And that principle, that mathematical principle, can be used. So given a situation, you can calculate one when you know the other. Okay? So the third part of this is the mathematical application of this concept. Okay, so what I'm going to do is I'm going to walk through a couple of problems. I'm going to put a question over here. I'm going to erase the stuff that we're doing because we're already on number 3. I'm going to put up a question, and then over here on the other side, I'm going to go through the answer and the theory behind it all. So my first question, or I guess situation, what I'll do is you have to suspend your questions right now about, well, how do we go about doing that? Like I'm going to say something like in a lab, the hydronium concentration was this amount. And your brain might say, well, how do you know how much it is? You will learn fairly quickly that we can do that in a lab. Like you can actually determine what those concentrations are. So it's not so far-fetched that we would know these numbers. I'm not there with you yet. Okay, so we will get there. Okay, so first question. So the first question, we'll use this mathematical relationship. So a solution at 25 degrees Celsius has hydroxide concentration equal to Okay, so solution at 25 degrees, and that at 25 degrees is critical, because if I didn't say at 25 degrees, then you wouldn't be able to use kW as 1 times 10 to the negative 14. So if it said a solution at 60 degrees Celsius, well, you'd have to look up what the value of kW is. You'd look up in a data booklet or something like that. But I'm saying at 25 degrees, so you can use the constant value that you have memorized. Okay, so a solution at 25 degrees. 25 degrees, 1 times 10 to the negative 14, it's a solution. So the assumption here is that our solvent is water. Later on, you might be using other solvents, and so all of this kind of gets thrown a little bit for a loop. But if you have water as your solvent, that means that the solution has water doing its equilibrium thing, right? Like, that's kind of what it's doing. It's doing this over here. It's doing that equilibrium. So we can apply what we know to this equilibrium. So it says the hydroxide concentration is 2.5 times 10 to the negative 4 molar. calculate the hydronium. Okay, well, let's use what we know. And I'll come over here, and I don't have to erase very much because this relationship is what we're going to use all the time. So that equilibrium has the K expression of Kw equals hydronium times hydroxide. We know 2 parts of that 3-part equation because the question told it to you. So a solution at 25 degrees, well, the first thing that you know is in your head, and that's 1 times 10 to the negative 14. That's Kw. The second thing that's in the question is obviously the hydroxide concentration. So we plug in and we solve for hydronium. It's really that simple. So I'll write it down. So here's my K expression. I know I have my students do it. I'm sure your teachers are kind of the same way. Write down the equation, the formula that you're going to use. Demonstrate that you understand, here's the relationship just in general, and here's me applying that relationship to this situation. Okay, so always start with that little formula. So here's my little formula, and then I plug in what I know. So Kw 1.0 times 10 to the negative 14. You don't have to put a unit with it because equilibrium constants, even though they have units that are related to molarity, we don't have to write them down because we know that the concentrations are always in molar. So when we solve, we already know that our answer comes out in units of molarity. So that value, that constant, equals the hydronium. We don't know because that's what we're being asked for. And then the hydroxide concentration is, from the question, 2.5 times 10 to the negative 4. So now it's algebra. So I solve that by dividing by 2.5 times 10 to the negative 4. So just so it fits my eye, like I like to, my algebra, I don't know, I grew up learning that the variable goes on the left-hand side. So that just fits my eye. So you'll see me do this all the time. So I'll kind of pretend that this was over on the other side. So the hydronium, the hydronium concentration is going to be the Kw divided by the hydroxide. So 1.0 times 10 to the negative 14 over 2.5 times 10 to the negative 4. Now, you can do that with a calculator. Sweet, good on you. If you can't, if you can do that without a calculator, then great. But if you can't, which, most of us can't do it, so you pull out your calculator. And a common mistake is if you're dividing by scientific notation, something in scientific notation, be very careful that you know how to use your scientific calculator. Okay, whether it's a graphing calculator or just a regular scientific calculator. Be very careful because it will only do what you tell it to do. So, for example, you might punch in 1 times 10 to the negative 14. And maybe you're not used to using the scientific notation button on your calculator. And so you go 1 times 10 to the x, and you put in negative 14. Divided by, you'll probably hit divided by, and then you'll probably do it again. 2.5 times, then you'll hit 10 to the x button, negative 4. Well, what your calculator will do, because you told it to, is to take 1 times 10 to the negative 14, that's fine, divided by 2.5. But as soon as you hit the times button again, it does that math. It does 1 times 10 to the negative 14 divided by 2.5. Gives you an answer. Takes your answer and then multiplies it by 10 to the negative 4 because that's the last thing you told it to do. So you have to be very, very careful when you're using your scientific calculator. You have to put, sometimes if you're not using scientific notation, the actual button on your calculator to do this, like the EE button or the EXP button, make sure that you put brackets around things. Okay, so make certain that your calculator knows the 1 times 10 to the negative 14 is a number, and the 2.5 times 10 to the negative 4 is a number unto themselves. So they're not separate entities, okay? So on my calculator, what I can do is I have a scientific notation button. So I go 1 times 10 to the negative 14 divided by, and then I put a bracket. Okay, so I'm going to put a bracket because this calculator is kind of weird for me. 2.5 times 10 to the negative 4, then I close the bracket so that it knows that I'm doing that. Okay, and so my calculator gives me, and it makes sense with what my brain would say, so it gives me 4 times 10 to the negative 11. Is that correct? Okay, so just using your very basic mathematical skills. Forget the part out in front. So if you had in math, 9, I guess, if you had 10 to the negative 14 divided by 10 to the negative 4, what would you do? You would, well, the bases are the same, so you'd subtract the exponents. So negative 14 minus negative 4, negative 14 plus 4, negative 10. So just that part is negative 10. 1 over 25, well, that's a fraction less than 1, so it kind of makes sense that you're in the neighborhood that it should be somewhere around 10 to the negative 10, 10 to the negative 11. It should be in that neighborhood. So you should be able to get a very logical sense of, is this the right number? If you got 10 to the negative 18, or 10 to the negative 19, I think it would actually be, that means you did it wrong. Like it's 10 to the negative 14 divided by 10 to the negative 4 should not go to 10 to the negative 18 or 19. That's too small. It should have gone the other way. So you need to use your math logic sometimes just to make certain that you're getting the right number. Okay, put brackets around your scientific notation and that will, generally speaking, solve all your answers or solve all your problems. This is also not the fully correct answer because 1, we haven't put a unit on it. We need a unit because without a unit, what does it mean? And 2, we haven't really paid attention to significant figures here, and I know everyone loves significant figures, so we need to make sure that we're doing that. So let's talk sig figs first. So this 4 has 1 sig fig. 1.0 times 10 to the negative 14, the 1.0 is 2 sig figs. The 1 and the 0 they're both significant. And then 2.5 also has 2 sig figs, which means that you're allowed to have, not allowed to have, you must have 2 sig figs in your answer. Well, a nice round 4 is not 2 sig figs, it's 1 sig fig. Well, it's 4. I mean, how do you change 4 to having 2 sig figs? Well, you probably know. You're in Chem 12. I'm hoping you know. The 4 is actually written as 4.0. Times 10 to the negative 11. And then to make sure that that has a unit on it that makes sense, that we're talking about a concentration here. So that is molar. And so in a solution that has, at 25 degrees, has hydroxide of 2.5 times 10 to the negative 4, it has a hydronium concentration of 4.0 times 10 to the negative 11. That's a small concentration. Now I want you to stop and I want you to think, do those numbers make sense? And so if you're thinking about Le Chatelain, you're thinking about kind of what all these numbers are doing. Number 1, this number, the hydronium, and the number for the hydroxide. Okay, so that 2.5 times 10 to the negative 4. Those two numbers multiply together to give you kW. So from that perspective, yeah, they make total sense. But does this make sense from a Le Chatelain perspective? So you've got a hydroxide of 2.5 times 10 to the negative 4. Let's think about this for a second. If you had distilled water at 25 degrees, what were the hydroxide and the hydronium before anything was added? Okay, well, they were, this number hopefully is in your head too, 1 times 10 to the negative 7, the square root of the kW. So 1 times 10 to the negative 7 is kind of the starting point. If you have pure water, that's at 25 degrees, that's the concentration you have. The question is said that there is a solution with a hydroxide that's 2.5 times 10 to the negative 4. 2.5 times 10 to the negative 4 is bigger than 1 times 10 to the negative 7. So whatever the scenario was that I gave you up here on the board, I added a base. There was something that made the hydroxide go higher than what it typically is in just pure water. And so, thinking Le Chatelier, okay, so if my right hand is the hydroxide and my left hand is the hydronium, they're going along, I'll go the other way, they're going along, and then the hydroxide spikes up, okay, and that's what the 2.5 times 10 to the negative 4 is that spike up. Then there's a shift and they both go down equally, and then they come back to equilibrium. So the hydroxide, when it finished, is that exact number. It's that 2.5 times 10 to the negative 4. Well, the hydronium's no longer where it was. It's dropped down below where it started. So it started at 1 times 10 to the negative 7. It has dropped down to 4.0 times 10 to the negative 11. So it's gone down. Hydroxide's higher, hydronium's lower. They still multiply to the same constant value. It's kind of a critical part of this. And so what you can kind of say to yourself is, well, here's my general equilibrium expression for water. If I know 2 parts, I can figure out the third one, no problem. I just need to know them. KW at 25 degrees is something that you have in your head. So you kind of always know that one at 25 degrees. It's almost not unknown. It kind of is known. And then if you're given hydronium or hydroxide, you can figure the other one out really simply. It's just math. Kw divided by the one that you already know. You can twist this a little bit. Okay, so I'm going to give you a different type of question, which is kind of a higher order type of question, and it has to do with water at different temperatures. So I'm going to write down a little scenario here. And there's going to be several questions actually that come out of it. So here's the scenario. Distilled water heated to 82 degrees Celsius. So we're not at 25 degrees. It's heated to 82 degrees Celsius. Has a hydronium concentration. Again, experimentally, there are ways to figure this out. So if you're saying, how do you know that? There are ways, we'll get there. Of 5.1 times 10, times 10 to the negative 6. 5.1 times 10 to the negative 6. 1. So the first question we need to ask ourselves is this. Is the water acidic? Now, where is that question even coming from? Well, I've said that the hydronium concentration is 5.1 times 10 to the negative 6. Well, you've got that number in your head of 1 times 10 to the negative 7. And so this value is higher than that value. And so one of the questions that people oftentimes have will be, well, if the hydronium is higher concentration than that 1.0 times 10 to the negative 7, if that's true, then isn't it acidic? Because that's what you said, the hydronium is greater than the hydroxide. Well, that would be true if it was greater than the hydroxide. It's greater than what it was before, but let's look at this a little bit more. Let's go to some other questions. So, is the water acidic? 2. What is the value of Kw at 82 degrees Celsius? Equilibrium constants are always temperature dependent. So at 25 degrees, we know what it is. At 82 degrees, we don't know what it is. So can we calculate it given the information that I gave you up above? And 3, is the water equilibrium endothermic or exothermic as written. Ooh. So this is going to take us back to, we're going to combine here a little acid and equilibrium theory, okay, with Le Chatelier and trying to figure this one out. Okay, so let's answer the first question. First question says, is the water acidic? So, is the water acidic? The most important thing that you have to see here is distilled water. Okay, that word distilled water means nothing has been added to it. It is pure, unadulterated water. Like, that's all it is. It has nothing else in there. There's nothing producing extra hydronium or hydroxide. It is just the water. So if water molecules only have other water molecules to bump into, the only thing they can do is that reaction. That's the only thing they can do. And if that's the only thing they can do, then whatever hydronium gets made, there has to be another, there has to be a hydroxide to match it. So even if the hydronium is higher, it's at 5.1 times 10 to the negative 6, higher than its regular 1.0 times 10 to the negative 7, the hydroxide will also be higher. So not only that, it will be higher and it will be the exact same value as the hydronium. Okay, so the answer to question number 1, is the water acidic? No. Hydronium and hydroxide are still the same value. They're both 5.1 times 10 to the negative 6. Therefore, it's still neutral. Okay, so the word distilled, it's going to be neutral, even if your hydronium is doing something that looks weird. Second question, what is the value of Kw? Well, if this is our K expression, okay, and Kw is, you calculate Kw from knowing the hydronium and the hydroxide, well, it's 82 degrees Celsius, so now we don't know Kw. Like, that value of 1 times 10 to the negative 14 doesn't apply. It's not 25 degrees. So, do we know the other two parts? Yeah, based on that logic, we know the hydronium because it was given to us. 2, it is distilled water, which I just mentioned, that the hydroxide has to be made in a 1-to-1 ratio with the hydronium. And so whatever the hydronium is, the hydroxide has to be the same value. So we know both of them. They're the same value. So the value of Kw is calculated by 5.1 times 10 to the negative 6 times 5.1 times 10 to the negative 6. And so if you take 5.1 times 10 to the negative 6, okay, so I'm going 5.1 times 10 to the negative 6, and I am squaring it. I get 2.6 times 10 to the negative 11. And I just made those numbers up off the top of my head. That's probably not what it is. But the concept is those two values have to be the same because it's still distilled water. To get the Kw, you multiply them together, and there's your new value of Kw. Once you know it, you can take it back and apply it into this. So if you have water at 82 degrees, you can use that constant value for any other calculations. Okay, so because it's constant, temperature dependent, so at 82 you can use it. If we go back to water at 25 degrees, you go back to using 1 times 10 to the negative 14. The third question, is the water equilibrium endothermic or exothermic as written? So this is more of a Le Chatelier question than anything else, but you have to kind of, one, know the water equilibrium and then understand what happened to the concentrations. So I'm going to remove this. I'm actually going to remove that too. Okay, so what do we have here? So here's our equilibrium right here. So what we have is we have an observation. Okay, so this value right here, that value right there is an observation. It's the result of something. Well, it's the result of what? Well, we heated it. Okay, if you kind of consider water at 25 degrees, kW is 1 times 10 to the negative 14. Hydronium and hydroxide are 1 times 10 to the negative 7 molar. If you consider that the starting point of everything, and then you go from there, and you say to yourself, okay, so 82 degrees is higher than 25 degrees. Therefore, we heated the water. We took distilled water, got a beaker of distilled water, put it on a hot plate, heated it up, hit 82 degrees. We measured how much hydronium was in there. So what did the heat do? Well, the heat created, as it does with equilibrium, it causes a Le Chatelier shift. So the observation that the hydronium is higher should tell us what that Le Chatelier shift was. So you have to kind of work backwards in time. So this value going up was not the stress, it was the result. So the shift had to have gone towards that side. So if I go like this, this was the shift as a result of heating, meaning from 25 degrees to 82 degrees. So that's what we observed. We observed it, the concentration of hydronium going up. Therefore, when we heated it, it must have shifted towards the hydronium and the hydroxide equally, because that's what the numbers showed us. And that's the only way that you could have got those numbers going up. Well, when you heat something, typically what happens? Not typically. What happens is it shifts away from where the heat term is. So it has to do with rates and activation energy and all that kind of jazz, which gets into a lot more detail. But the kind of the quick and dirty way of figuring it out is when you heat something, it shifts away from the heat term. So if it shifted that way, if it shifted towards the right, okay, and it's shifting away from the heat term, that means the heat term must have been over here. So that's where the heat term was. Now, if the heat term was over there, on the reactant side, that means water's equilibrium had to have been endothermic as written. So it's endothermic, you heat it up, it shifts over to the right. Hydronium and hydroxide go up equally, so it remains neutral. And whatever they go up to, that's kind of what the new hydronium and hydroxide are going to be. Okay, so that's today's class. Tomorrow, or next class, I guess is not necessarily tomorrow. Next class is going to be how does pH and pOH kind of fit into all of this, because that's kind of what we know about acids and bases, right? We know the pH scale, and we know that 7 thing, which is going to get thrown for a little bit of a loop here now that water is temperature dependent. But pH and pOH are related to the hydronium and hydroxide concentrations. So that's where we're going. We need our calculators. We need to know how to do logarithms. So we'll need our Math 12 knowledge to kind of get incorporated into here. And if you don't know, you're not in Math 12, or you don't know how to do a logarithm, I'll try to show you on calculator. And it's just finding the right button and putting in the right thing. It's not super complicated logarithms. It's just once you get the mechanics of it, it's pretty straightforward. Okay, so we'll see you next class.